Okay, all right. Let's get started. These are the definitions we have discussed with reference to characterizing amplifier. We have seen this in the last class, how to characterize an amplifier and what are the important relations that come across while characterizing the amplifier. And this is simple diagram we have shown with reference to the amplifier. Instead of writing entire circuit for the amplifier, we just represented an amplifier with a triangle symbol and all the input signal, output signal, the resistance. So all those other things we have shown here. Okay. Later we have shown the equivalent circuit of the amplifier, which is here, and with reference to this, we have arrived at different equations that characterize the amplifier. We need to know the definition here. Input resistance is it's input voltage by input current. That's the definition. This definition, see, we have to apply for different circuits. This is a basic definition which we need to be aware. And with reference to this amplifier, we should know where we are measuring the input signal. Okay, so you can see here there is an input signal here, Vi, which goes to the amplifier. So Vi can be denoted as amplifier input, and V signal is the signal source. And Vi, V signal are related by voltage division rule, which is given here, as you can see here. So Vi is equal to V signal times Rin divided by Rin plus R signal. And another parameter which we need to be aware is open circuit voltage gain AV naught. This is the definition, V naught by Vi. Under the condition, RL is equal to infinity. And to measure the output resistance, we need to connect a temporary voltage source labeled as Vx that provides current as Ix at the output terminal. As you can see in the circuit here, we have connected a temporary voltage source across the output of an amplifier, and that gives us the current Ix. The ratio of Vx, temporary voltage source, with what the voltage that it provides to the current that is coming out from the temporary voltage source. Okay, so that gives the output resistance, provided input signal must be 0. This is the experimental setup to measure output resistance of any amplifier, not only for this amplifier, for any amplifier. This is how the experimental setup we should do. Okay, probably in the laboratory, I think we are setting the input signal and connecting an impedance box here, and we keep varying the impedance box so that when output falls to half, so we see the resistance box, and the value of the resistance box gives you the for which output signal dropped 50%. That gives the output resistance. Let's say a trial and error method of finding output resistance of an amplifier. But actual method is this. So connect your input resistance. Let's circuit everything of whether it is a CA amplifier or CS amplifier with reference to MOSFET. The circuit should remain same. The only thing is you are not applying any input signal, but we are connecting a temporary voltage source, a DC voltage source, and you can apply here some temporary small voltage. Say for example, 2 volts you can apply and see how much current is coming from this temporary voltage source. You can measure the current, and you can also measure how much voltage we have applied. The ratio of this to this gives the output resistance of this amplifier. This is the experimental setup which we need to uh, have while measuring the output resistance of an amplifier. Okay, so that is the output resistance, and later we have shown the equations related to the V naught and Vi. So this is a Thevenin's equivalent circuit. V naught is equal to this is the output voltage of an amplifier into RL divided by RL plus R naught. So this is derived from the equivalent circuit that we have shown here. So this is from this equivalent circuit we can write output voltage using Thevenin's theorem. V naught is equal to this AV naught into Vi multiplied with RL divided by R naught plus RL. So the same equation is used here. Okay, so this is a Thevenin's equivalent circuit. Okay. so this is from this we can easily arrive V naught and Vi relation. Okay, so V naught by Vi is nothing but the voltage gain, which is AV. Okay, so AV and AV naught, so you can substitute using equation 5 in the equation 6 you can use here. AV is nothing but it is a V naught by Vi. Okay, so you can use in the equation 6 to obtain that's for V naught you can substitute here, and you can obtain the equation for AV also. AV and AV naught, that's how they are related here. Okay, finally we have overall voltage gain, which we denote it as GV. Okay, so this is the definition V naught by V signal. This is the definition for overall voltage gain, and you can substitute for V naught and Vi. Okay, so Vi you can arrive at this equation by from the V signal, and this you can substitute it here for V naught and Vi. So after simplifying, we have shown this in the last class. We arrive at this equation. Next, we have discussed about the. We need to discuss, the different amplifiers. The first among them is common source amplifier. Shortly, we denote this as CS amplifier. There are totally three mass configurations. One of that is going to be the common source configuration. Using common source configuration, we can develop an amplifier. The circuit is as shown here. Okay, this circuit may not have all the elements of amplifier, but only we are doing an analysis here. We just have only the component required for to characterize the amplifier. As you can see here, the signal V signal that needs amplification is fed into the MOSFET, and this R signal represents the internal resistance of the AC source, and here we have an Vi, that is an amplifier input signal. Okay, so Vi and V signal, they are related by the voltage division rule. Vi is equal to V signal times the Rin divided by Rin plus R signal. That's how it is related. Okay, so you should know these relations here, how this Vi and V signal, how they are related. It's very simple by using voltage division rule. So Vi which is equal to V signal times Rin divided by Rin plus R signal. Remember, this is Rin. Rin means it is input resistance. So this is signal resistance here, internal resistance of the power supply here. Okay. So these two are related using this based on this relationship, which is voltage division rule. Okay. So and other things in MOSFET, all the time you need not write different terminals here. So you can just whenever it is, if you have any confusion, you can write the terminals. Otherwise, it's implicit that since it is a common source configuration, we will have a source here, drain is here, and we have a gate here. Okay, so and the resistance which we connect to the drain is labeled as RD. So this is a drain resistance, and we measure output of this common source amplifier across the drain and the ground here. Source is grounded, so wherever you find ground, that's going to be the source. So we have a source here and a source here as well. So wherever there is a ground, that's going to be the source, because this is also called as a grounded source amplifier. Okay, so now we have a resistance here to measure the output voltage, which is V naught of the amplifier, and output resistance can be measured by seeing across these two terminals here, this drain terminal and the source terminal here. So this is the complete amplifier circuit here. Okay, so excluding the capacitors is what we have shown here. Now to simplify this or to do analysis on this, now we have to write an equivalent circuit of an MOSFET, and then you can write various parameters, equations for various parameters. Okay, so that's very simple. So we know MOSFET equivalent circuit according to hybrid phi model, which is shown here, and we can attach other terminals, other components to this equivalent circuit as per the circuit diagram. As you can see here, once we replace MOSFET with its hybrid equivalent to the gate, there is the R signal and V signal, as you are seeing here, and at the drain point we have a drain resistor, as you can see here, and the source is straightaway it is grounded here. source is grounded. So this is the equivalent circuit of common source amplifier. So without RS, there is no RS as such here. So we including RS, we have a different circuit. We will discuss that later. Now based on this, so since this is going to be an equivalent circuit for the common source amplifier, based on this we can do an analysis. In the sense, we need to find input resistance, output resistance, voltage gain, open circuit voltage gain, the normal voltage gain, and then the overall voltage gain. So those equations we need to derive for this. So I don't want to go for more derivations of this since we have done this in the last class. I straight away remind you here to uh, uh, remember the expressions here, so that that is useful to solve the problems, because when the problems are asked in the examination, you cannot keep deriving parameters, so that it becomes difficult for you to solve the problem. So therefore just remember the equations. So for common source amplifier without source resistance, input resistance is infinity. Yes, I'll put a box, so that those things you need to remember. Okay, so this is the open circuit voltage gain for the common source amplifier. These are the formulas which you need to remember. Remember, there is a negative sign here, minus gm times rd parallel with rn. It's very easy. If you can if you look at the circuit, we can easily write this v naught equation, right? So looking at the circuit, what is v naught? V naught is nothing but current times the resistance, right? This is the current which is going out from the drain terminal. So minus gm times vgs into this two parallel combination of resistances, as you can see here, parallel combination of resistances here. So v naught is nothing but this is the current and this is the resistance here. So it's very simple. Okay, so you can easily arrive at v naught by vgs, which is minus gm times rd parallel with r naught. Output resistance, as you see from the drain and the source, this is a drain terminal and this is a source terminal here. If we observe from here, there's arrow mark is showing that observe drain and the source. So this is output resistance rd. R naught is nothing but rd parallel with r naught. So do not get confused with this. So this is r naught here. So we denote this as RO, okay, which is nothing but RD parallel with R naught. So this R naught is going to be the internal resistance of the MOSFET when channel length modulation effects are considered. So this R naught comes into play. Okay, this you must remember, R in AV naught and R naught, and finally AV naught. So AV naught is nothing but which is transistor output resistance under this condition. So when we assume that R naught is very large compared to the RD, so this basically this R naught resistance reduces the magnitude of voltage gain, so we can ignore this. So when we do that, this equation for AV naught reduces to this. Okay. Rather than remembering the approximated equations, you need to remember the complete equation. So these equations, complete equations, are required to solve the problems. Okay, so this is an approximated. So once we do this assumption, so you end up with this kind of approximations. So this is AV naught actually. This is subscript here. So this is A and V naught here. This is how we need to represent here. Should not write this as AV like this. A and V is subscript. Another subscript is going to be the V naught. So that's going to approximate this is equal to minus GM times RD. Okay, so finally the output resistance, if R naught is ignored, so R naught becomes equal to capital RD. Okay, so that means output resistance depends on the external resistor that we have connected between drain and source. Next is overall voltage gain. It's very simple equation. Overall voltage gain we denoted with GV, if you remember that. G is gain and V indicates it is overall voltage gain. There's a lot of difference between AV and GV. Okay, so AV is nothing but which is V naught by VI. So it is an amplifier output by amplifier input. That is AV, voltage gain. Whereas GV is nothing but it is overall voltage gain, which is nothing but V naught remains same, but instead of VI we will have V sigma. That is the difference. So this is the definition for the overall voltage gain. Gv is equal to V naught by V signal. Now look at this, since input resistance is infinity for this common source amplifier, that means input resistance is infinity means, so the entire signal will appear at the amplifier input itself. To understand this, you need to look into the circuit. What do you mean by that? Okay, so here, as you can see in the equivalent circuit, this input resistance, when we see from the gate to source, is infinity because of there is an open circuit in the MOSFET between gate and source. Due to that, since input resistance is infinity here, there is no current flow. Okay, because once the resistance is infinity, there is no current flow here. Current doesn't flow, but we are applying the voltage here, signal voltage, which is V signal. So now this complete V signal appears across this VA itself here because there is no current flowing here. So I becomes 0 here because of the infinite resistance here. So therefore the complete V signal appears across the VI. This is applicable for this circuit. As long as this Rn is infinity, for that kind of circuits, this V signal becomes equal to VI. VI and V signal are same for this, provided this Rn is equal to infinity. So we can write here this is V signal for the circuit is also equal to Vi amplifier input, and the AC signal that we apply becomes equal because this is Rn is equal to infinity and there is no current flow in the gate terminal. So we can write the Vi and V signal both are same. That is due to the fact current is not flowing through the R signal resistance. So also this Rn, as long as Rn is equal to infinity, this condition holds good. Now we can consider the load resistance and we can also calculate overall voltage gain. So AV, we know that already. So AV is nothing but which is minus GM times RD parallel with R naught parallel with RL. Just now I have shown this. So you can see that AV naught is here. So AV naught is minus GM RD parallel with R naught. We can consider load resistance, and based on that we can also write the overall voltage gain as RD parallel with R naught parallel with RL. Since Vi and V signal both are same for the common source amplifier, so we can substitute here V naught, and in place of Vi we can also write V signal, we can also write Vi. Remember, this is the definition for Gv and this is nothing but Av. So for this circuit, Gv and Av both are same. Okay, so that's why we can write here, since we know that Av is equal to, including this RL, Av is equal to minus Gm times Rd parallel with R naught parallel with RL, so that we can also write Gv is equal to Av minus Gm times Rd parallel with R naught parallel with RL. So we can also, looking at circuit, we can also write directly this Av and Gv. Av is based on the fact of this equation. So we know that this is a basic output voltage equation. So we know that this is AV naught. AV naught means there is no RL here. Okay, AV naught means it is a definition is V naught by Vi with RL is equal to infinity. Whereas AV is nothing but the same definition, V naught by Vi, whereas we are not going to make here RL as infinity. RL is now not equal to infinity. Okay. Now once you remove this, once RL is included without making infinity, this equation changes now. Here we need to add another parallel combination. So therefore AV becomes now, okay, AV becomes now the same equation, minus Gm times Rd parallel with R naught parallel with we will have an RL. Okay, so this is a change what you have seen here. We already have AB naught equation without RL, but with RL this is going to be the equation. But observe here, for this common source amplifier, AV and GV are same. Okay, so that's why you can write this straight away. If you observe it clearly, you will get to know that AV and GV are same. So minus GM into this complete term. Okay, any questions about all these derivations? I hope you have understood the derivation. Okay. If there are any questions, I would like to take up. So this all these formulas that we have highlighted in the box, you should remember them. Now let us move on to the observations what we have done here. Input resistance Rn is infinity. That's one of the important property of a common source amplifier. This shows that Rin is infinity. It's one of the good property of this amplifier, because see the when once Rn is infinity, the small signal is directly fed into the amplifier input. Okay, so that is the conclusion we can arrive at as long as this Rn is equal to infinity. In fact, this is going to be the good property of an amplifier. Any amplifier, the input resistance must be very very high. Output resistance, we expect that to be uh, low, but here you can see and observe here, there is a moderate to high resistance. Output resistance keep varying from moderate level to high level. Okay, so somewhat better compared to other amplifier circuits. If you look compare this with other amplifiers, output resistance also is very high as similar to the input resistance, but we expect output resistance to be as small as possible, but here it varies from output from moderate to high. Okay, but this is not going to be a serious effect, but having lower output resistance is always good. Third one is the open circuit voltage gain AB naught that we already showed with RL is equal to infinity can be high. Okay, that's the advantage for us, open circuit voltage gain. Open circuit in the sense when there is a huge load connected to this amplifier, at that time this open circuit voltage gain is very high. Okay, so that's an advantage for us. And of course, this is the circuit is limited by the bandwidth. Common source amplifier doesn't have an infinite bandwidth. It is limited by the bandwidth. What do you mean by bandwidth is limited? That means there is an upper cutoff frequency limit if U, what we say, there is a lower cutoff frequency limit if L. So that means signal is provided good response between these two limits. Okay, so we will discuss that when we come to the frequency response of an amplifier. Okay. Okay, let us take up this problem. So, though we solve here few worked example or exercise problems, students should not stick to these problems. Students should solve different problems from the textbook itself. Okay, so this is a simple example, which we are solving here to make you to understand this topic. Look at this problem. Try to understand this problem thoroughly so that we can solve this using the formulas that we are already aware. Consider common source amplifier with a drain current flowing as 0.25 milliampere. Look at this. You have to highlight given data. You can write down the given data at one point, which we have done here. So ID drain current is 0.25 milliampere, which is given, and the type of amplifier is common source amplifier. VOV. So OV means it's overdrive voltage. You have to be careful about this. Overdrive voltage is given as 0.25 volts. What is overdrive voltage? If you look at our fundamentals of MOSFET, so overdrive voltage is nothing but VGS minus VT. VOV is nothing but VGS minus VT. This is called overdrive voltage. By we denote this with a simple notation, which we call as a overdrive voltage. The excess voltage to drive the MOSFET, that's called overdrive voltage. So in this problem, it is given as 0.25 volts. That's the overdrive voltage. And let us look at into other parameters like drain resistance is given as 20 kilo ohm. This is also important. VA. What is VA? If you observed, in our analysis, there is something called early effect. So this is an early voltage VA, which is given as 50 volts. Okay, so due to the channel length modulation effect, there is early voltage will result, and that gives a value of 50 volts. Signal resistance is given as 100k or signal. It is the internal resistance of AC source, and load resistance is given as 20k. And here we need to find R in AV naught, R naught, and AV and GV here. So these are the different parameters which we need to find here from this problem here. Okay. And also there is another condition that is given in this problem. If to maintain reasonable linearity, the peak of the input sine wave signal is limited to 10% of 2 times overdrive voltage. What is the peak of the sine wave voltage at the output? As I told in the beginning itself, the problem need to be thoroughly understood. Otherwise, what happens is if you have limited information, and with less understanding, we cannot solve the problem. So let us see here what is that condition it is said here. If to maintain reasonable linearity, that means in order to maintain the linearity, reasonable value of linearity. What is linearity? Linearity is nothing but a straight line between the input and output. Suppose if you have a characteristic something like this is called as a linearity. If it is an Vi plotted along x-axis and a V naught, it is plotted along y-axis. Okay, so then the curve that what we plot here, a straight line, a 45-degree line from the origin. So this is called linearity. What it is said in the problem, how this characteristics is related to this problem. So what it is said in the problem is, if to maintain reasonable linearity, that means the device should maintain linearity, because entire characteristics of a MOSFET is non-linear. Some portion is going to be linear. We have seen in the beginning of the discussion. Okay, so in order to maintain reasonable linearity, okay, so in the output and as well as input, linearity means you have to maintain the output signal proportional to the input signal. That is the meaning of linearity. To maintain that reasonable linearity, that means when we want to maintain output signal variation corresponding to the input signal, the peak of the input sine wave signal is limited. We need to restrict our input signal to 10% of the 2 times overdrive voltage, okay, to maintain this linearity. Then for corresponding, when we apply input as 10% of 2 times overdrive voltage, it is asked here, what is the peak of the sine wave voltage at the output? So it is asked here, what is the output voltage peak of sine wave that is resulting from the amplifier output, that we need to uh, obtain here from when the input signal is limited by this 10% of the two times overdrive voltage. So we'll come back to this last part a little later, but other things we can easily find out from the formulas whatever we are familiar with. Once again, I repeat here, once you read the problem here, write down all the given data as it is written here. You can see drain current is given, overdrive voltage, drain resistance, early voltage, signal resistance, load resistance. So all this data is given right down here. And let us solve one by one here. So now we need to find out input resistance Rin. So we know by default, while doing analysis, the input resistance is infinity. So you can write straight away, input resistance is infinity for this. Okay, though it is signal resistance is given as 100 ohm. So this Rin itself is very large here, so there is no current flow through this, so this cannot be considered. So Rin is equal to infinity here. Next is, let us some formulas see we might not derive, but you need to be aware of this. You should remember that. Write down these formulas at the end of your notes so that you don't forget while solving the problem here. So this is a relationship between MOSFET output resistance, internal resistance, to that of the early voltage and drain current here. So R naught is equal to modulus of VA by ID here. So this is the equation which you need to remember here. Okay, again see, this comes under the fundamentals of MOSFET here, though it's not there in the syllabus, so you need to remember this type of equations here. So R naught is nothing but MOSFET output resistance due to the channel length modulation effect, and there is a VA by ID, modulus of VA, because VA is going to be negative. If you remember that in our classes, the early effect we have highlighted when we plot the characteristics of a MOSFET, something like this, okay, with reasonable value of slope like this, without writing them as a straight line. When we extend this as a to the negative axis, you have seen that the early effect, at some point all these curves will meet, right? That voltage is nothing but VA. Okay, so that is called early voltage here. So now the output resistance here of this curve, okay, this is nothing but the graph of VDS versus ID. This is VDS versus ID graph. Okay, the ratio of this gives you the slope of this, gives you the inverse of this slope, gives you the resistance, which is nothing but R naught. The R naught and the early voltage are related by this equation here. Okay, so if I expand this curve here, the curves will be something like this, and slope of this curve what I am showing here, is nothing but it is delta I by delta VDS. So this is delta ID on delta VDS. So the inverse of this slope gives you the output resistance, which is R naught. So R naught here is also related to the early voltage, that is what we have shown here, which is VA by IT here. So this effect is called channel length modulation effect here. Okay, so this is the formula based on that. So in this problem, so we need not go to that much of analysis, but if you know this equation, you can just substitute here VA and ID. VA is given as 50, as you can see here, and ID is nothing but 0.25 milliampere. Okay, so substitute here and find out the value of R naught is going to be 200 kilo ohm. Okay, so remember that R naught value will be very large, so this will suppress your voltage gain in the common source amplifier. Okay, that's why we ignore this, since this is going to be the parallel combination with drain resistance. So in the output, as you observed, R naught is always appears in parallel with RD. Okay, so since this is going to be very large, in parallel combination, a larger value can be ignored. Okay, smaller value can be considered here. So that's why we ignore this value in most of our analysis here. Okay, so next let us find out the drain current, use the drain current equation in saturation. We know that MOSFET when operated in saturation region, this is going to be the drain current equation. ID is equal to half of Kn dash into W by L into overdrive voltage VOV square. Okay, so this VOV is nothing but I already told you, which is VGS minus VT. Okay, so VOV square. So this is the drain current equation in saturation. So this is, let me remove this and write this drain current equation in saturation. So this is the drain current equation in saturation. Okay, right here this is okay, so ID at saturation. So drain current at saturation. This equation can be terms can be rearranged. So let us cross multiply this 2 times ID on the left hand side, as you can see. On right hand side you can retain as it is Kn dash into W by L, and this square can be written as 2 times VOV. So VOV. Okay, it is repeated here because square here. And also we need to know the GM equation. GM equations we have discussed this many times. So GM equation is Kn dash into W by L into overdrive voltage. So this is a GM equation. If you compare this equation, some part we can substitute here, as you can see this Kn dash W by L into VOV can be substituted with GM. So this GM can be substituted here. So 2 times ID left hand side is kept as it is. Now in place of this we can write as a GM. So GM is written here and overdrive voltage is kept as it is. Now from this we can find out what is GM. GM is nothing but which is 2 times ID divided by overdrive voltage. So ID is given as 25.25 milliampere and VOV is nothing but 0.25 volts. So you can simplify this and you can arrive at GM. So GM is 2 milliampere per volt is the unit here. Milliampere per volt is the unit here for this, since GM is going to be very small for this. 2 milliampere per volt. That's going to be the GM transconductance value for this problem here. Next is R naught. R naught is nothing but RD parallel with R naught, small R naught here. So how do we get to know this? Look at the MOSFET equivalent circuit at the output side. So these are the two resistances that are parallel. So that is the output resistance of the common source amplifier. In this case, RD is given as 20 kilo. Just look at the given data. Okay, 20 kilo, which is given here, and R naught just it is 200. We have estimated here R naught is 200 kilo ohm. So R naught is 200 kilo ohm. So look at the total resistance is now, which is 18.18 k. You can also observe here in this problem, since R naught is going to be very large, which is 200 k, and look at RD, which is very small. And when we have a parallel combination like this, the net resistance R naught is nothing but which is almost equal to this 20k resistance here. Okay, so that's why we ignore this in our analysis here. Okay, you may ask a reason why we ignore this R naught here, because this R naught is a very large value since it is a parallel combination. Even if you see the easily we can arrive at the answer, even if you ignore here the parallel combination of this, the value of this is almost equal to this. Okay, this is just like analogy here when there is a parallel resistances like this. One is with a 200 k, other one is 20 k. If I have a current flow here and current here, suppose if I denote this as I and this as I here, now which path the current will choose now? Okay, obviously it must be the 20 milliampere, right? 20 k resistance instead of 200 k resistance. Current always looks for low resistance path here. There are two paths here. This is one path for the current flow. This is another path for the current flow. Okay, among these two paths, this path is offering very high resistance here. So this path generally will be ignored by this because of high resistance here. So current chooses this path here. Okay, so that's how the current flow will take place in this. Okay, so I hope you understood the significance of R naught here. R naught is only, it depends on RD. It doesn't depends on small R naught. It's a MOSFET internal resistance. You can vomit this resistance. Okay, so AV naught. Now the formula for AV naught, open circuit voltage gain, AV naught is given by minus GM times RD parallel with R naught. And again here once we ignore this or else you can we already know this value, which is 18.18 k. You can substitute here, and GM also it is no 2 milliampere per volt. So we can find out the value of AV naught. Open circuit voltage gain is minus 36.36. Since it's a voltage gain, there is no unit for this. Okay, so next is overall voltage gain. So overall voltage gain is also same as this AV, GV and AV both are same. Okay, only thing is here you need to include another parallel combination as RL. So which you can see here, RL has been included here. So now we can including this RL, we can calculate what is the overall equivalent resistance, and that should be multiplied with the transconductance, which is 2 milliampere per volt, and value is going to be negative here. So GV is nothing but minus 2 milliampere, and this equivalent value of this all this parallel combination is 9.523 k. Student should calculate all these things blindly. Don't write the values what I have shown here. So write down, calculate this and find out this value. This value leads to the 9.523 k, and now this multiplying that with transconductance minus 2 gives us the overall gain as minus 19.05. Observe that the gains with RL as infinity, which is AV naught, minus 36.36, which is very high. And now you observe overall voltage gain or voltage gain of the amplifier, which is 19.0, which is very less compared to this 50%. The gain has been reduced due to the inclusion of RL here. Okay, that's the thing you should make out here. Next is the critical part of the problem is as to maintain linearity at the input side. They are suppressing this, reducing the input signal by 10% of the 2 times overdrive voltage. Input signal for the amplifier is gate to source voltage. 10 per that's equivalent to the 10% of 2 times overdrive voltage. Let us calculate what is this value. 10% means it's a 0.1 into 2 times overdrive voltage is 0.25. That gives us 0.05. That means we are maintaining in order to have a linearity in the input output, the gate source voltage must be 0.05 volts here. Now here they are asking what is the output voltage. So output voltage now as per the definition, which is AV is nothing but which is V naught by Vi. This is the definition. AV which is nothing but which is V naught by Vi. In this case Vi is also equal to VGS. So this is equal to VGS. Now AV is equal to V naught by VGS, or V naught is equal to AV times VGS. Now we can just multiply this VGS 0.05 with the AV. Since this is a negative value, since output voltage cannot be negative here, you can use modulus to avoid negative sign. So 19.05 into 0.05, which gives you 0.9525 volts here. Look at this now. So to maintain linearity at the input side, we are limiting the sine wave peak to 0.05 volts, and that linearly, the value of output voltage is going to be 0.9525 volts. So this is the output voltage, uh, which is in linear with the input voltage here. Okay, so that's how the problem need to be solved. I think this we have uh, obtained all the things that is asked in the problem. Okay, so my suggestion to all of you is, whenever the problem may not be of as simple as this. Okay, it may be sometimes complex also. uh, do not be panic when the difficult problems are asked in examination. The only thing is, write down all the data and uh, remember the proper equations which need to be used in the problem, and then you can solve the problem very easily. If any equations are forgotten, or if equations is, if you make a mistake in writing equations, you will end up with wrong values. You should be careful while solving the problem. Okay. With this knowledge, I think you can solve other additional problems given in the textbook also. Any problems students are finding it difficult, you can bring it to my notice so that I can solve the problem and help you out in for the examination point of view. Okay, next let us move to the next type of amplifier, which is an important amplifier, an extension of previously what we have discussed. It's same common source amplifier with a source resistance now. Let us see the consequence of adding the source resistance at the source terminal here. Previously, what we have discussed is without having this. This was not there. Okay, so directly we have connected the source terminal to the ground. Now with having this source resistance here, what is its implication on the overall gain? So, any idea about that adding RS? What kind of whether it is a advantage or a drawback here? Any points you are familiar with? Any benefit you are going to get? So there must be some benefit, otherwise there is no point in discussion of this circuit by adding the source resistance to the source terminal of the MOSFET here. But I'm asking you, what benefit you are going to get by adding source resistance at the source terminal? How the circuit is better compared to the previous circuit? There must be some drawback in the previous circuit. What is the drawback? Drawback is, see, the problem is with transistor here, MOSFET here. MOSFET has got numerous parameters, and these parameters keep changing. Okay, so with reference to the input signal, or with reference to the the temperature and other things. So this variation of this transistor parameter should be kept minimum. So to achieve that, we have here something called as RS. When we add an RS here, abrupt increase in the drain current is controlled. We have seen this in biasing also. Okay, so RS provides negative feedback. By providing negative feedback, this RS compensates itself. Any increase or decrease in the drain current due to the change in temperature or due to the change in parameter of a transistor, this RS is going to compensate that. Suppose if any parameter changes, let's assume that that leads to the increase in the drain current, then the gate source voltage is decreased by this RS. Or any parameter that leads to the decrease in the drain current, let us say. Okay, so the now the RS will compensate the voltage here, and such that the decrease in this will be again increased by the input signal here. That means whenever the ID drops here, the gate to source voltage is increased by the RS, and whenever the ID increases here, and the corresponding gate to source voltage is decreased, so that output drain current is maintained constant. Okay, this is how the circuit balances here. Okay, so now let us go to the in-depth and analyze this circuit here. Common source amplifier with a source resistance here. This is the circuit diagram for the common source amplifier with a source resistance included here. So from, if you remember previous circuit, writing this circuit becomes very easier. Only thing is, you need to add a resistance at the source terminal here. Between the source and ground, you need to add a source resistance. That's only change. Okay. We will see the analysis for this circuit here. Okay, so this stabilizes the operating point of this transistor for any variations in the transistor parameter, the MOSFET parameters here. Now let us write the response signal equivalent for this circuit and uh, characterize the amplifier. I mean, we need to find out various parameters of an amplifier here. Okay, so let us see that how to write an equivalent circuit, which is shown here. You can see here. So replace this MOSFET with its hybrid equivalent circuit pi model. Okay, so when we do that, you can see the resulting circuit is here. So this is the equivalent circuit here. As you can see, this part we have already done. There is no change here till here. But look at here, the only thing is at source terminal we have added an extra resistance here. And this equivalent circuit we have already shown in the previous section here. Okay, so that's a common source amplifier. The only addition in the equivalent circuit is you need to add RS similar to the original circuit what we have done here. So you need to add in the equivalent circuit also that RS resistance here. Okay, now let us find out the various parameters of this. Okay, other things I need not explain from the original circuit to this. It's a self, it has come from this original circuit which has come to here directly. Okay, so we need not worry about too much about these things. Now let us find out each and every parameters of the amplifier. The first parameter of the amplifier is input resistance. As we know that for any amplifier input resistance must be infinity, even for this circuit also. Looking at this side from the gate and the source terminal here, if you observe from here, the R in for this circuit is also an infinity because there is an open circuit between the gate and source, therefore R in is equal to infinity. Next is we can obtain the expressions for the voltage gain. For that we need to uh, write the equation for the output voltage. Look at the circuit and you can write the expression for the output voltage here. Okay, so you can see here this is V naught is nothing but which is a current times the resistance here. So straight away we can write this current is going to be the GM it is going away from this drain terminal here, so which is negative. So we can write equation for this as minus GM times VGS, that is the current. This entire thing is the current here, including negative value, multiplied with the resistance is RD. So this is the expression for output voltage V naught here. Okay. So you can see here we have written the output voltage expression as minus GM times RD times VGS. The GM VGS is going to be the current and that multiplied with RD gives you the output voltage here. You can apply KVL, the between the gate and source loop and see what you get it here. Gate and source loop is this. You can see here. So we can apply KVL here and we can arrive at the mathematical, the KVL equation here between the gate and source loop here. So you can see, if you apply here, what is the equation you get here? Minus VI, I am starting from journey from here. I'm moving like this to the ground here. Okay, which is uh, this is VGS plus VGS. I can write here minus VI plus VGS. This is the loop I'm coming here. Now we have a drop across this. Drop across this is nothing but GM VGS times the RS plus GM VGS. This is the current times the RS. Okay, so this is the KVL equation. If we apply KVL from between the gate and the source loop here, you can simplify this and obtain the equation for here VI. So you can see here the same equation is written here. Okay, as you can see here, VI is equal to VGS. I can observe here. VI, if you transfer on the other side, get VGS plus GM VGS times the RS. The same equation that I have showed by applying KVL to the gate source loop, and VGS can be taken out as a common factor from these two. So get 1 plus GM into RS. So now we can write the equation for VGS, which is VI divided by 1 plus GM into RS. What do we mean by this? So this shows that voltage at gate to source is less by this factor here. So VI is nothing but input signal that is applied at the input here. This is a VI, and the moment the signal comes here, it is dropped by 1 plus GM into RS. So from here to here, there is a drop in the input signal by a factor of 1 plus GM into RS. This is since it is in denominator, there is a drop in the signal. Because of inclusion of RS, there is a drop in the signal. In fact, even though the input signal drops, our overall voltage gain also drops, but in other side you get benefit such as circuit compensates for the MOSFET parameter change. That's an advantage what we are going to gain from this. Okay, so thus we can use the value of RS to control the magnitude of the signal. So you can see here this magnitude of the signal can be controlled, uh, VGS especially can be controlled by varying the RS, and also we can ensure that so the proper the feedback is supplied so that the overall circuit is operated in linear manner here. Okay, so a non-linear distortion can be eliminated here. So by reducing the value of the VGS by controlling through the RS. Next is we will calculate another equation which is small signal voltage gain, which is AV, which is equal to V naught by VI, and V naught equation which we have already shown here, which is a V naught equation is here, so that you can write it here, and VI equation which you can just cross multiply this, you get VI equation also, which is VGS times 1 plus GM into RS. So you can observe here this VGS and VGS cancels here. So left out with minus GM into RD in the numerator and 1 plus GM into RS in the denominator. So the equation for AV is nothing but minus GM into RD divided by 1 plus GM into RS. Now the output resistance is very simple. Look at the circuit. Output resistance is just simply RD. Okay, so R naught is equal to RD. That is the output resistance of the common source amplifier with RS here. So finally we have the if load resistance RL is included, then what will happen to this AV value? Then along with RD and RS, RD, okay, so you will have an equivalent value which is RD parallel with RL here. Okay, so like this you can arrive at the different equations for this, and again there is one more problem which we will take up in the next class. Okay, any questions so far about derivation part of common source amplifier with RS? These two circuits are very important from examination sake. In the next class we are going to solve this problem, and finally we are going to take another circuit which is a common drain amplifier as our source follower. Okay, we again see we will analyze even this circuit, and then we will move on to the capacitance effects of the MOSFETs. Okay, I once again suggest every student to watch my videos. All videos are available in my channel. Okay, so students are advised to watch those videos and get prepared for the class. Okay. Okay, any questions about this? Today's class, are there any questions before we wrap up today's class?